In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 1, Introduction, Part 7. Now the question is, which theoretical models are best to predict the material's behavior? As you know, when we want to give an analytical solution or numerical solution to the problems, to any mechanical problems or any engineering problems, we have to model the behavior of materials, because the behavior of materials is very difficult to understand and it's very difficult to formulate. Therefore, we use simple models, very simple models to use in our equations, in our analytical solutions or numerical analysis. I try to present to you here some of these models. I start with elastic behavior. Okay? As you can see in this figure, we have sigma versus epsilon, and this is elastic behavior, which is very linear, and E is the modulus of elasticity. We can model this with this figure like here. We have a spring here and we have a force. If we apply this force, the spring stiffness is constant, and as we apply the force, it changes in length. In fact, we have deflection or change in length as the applied force is increased. And this E as shown here, because a stiffness, we have a stiffness for this, we have a stiffness for this. So we can model it with such a model and use it in our calculations. We call this perfectly elastic. Okay? So it's completely elastic, and when we apply the load, we get some changes in the length, and when we unload, it goes back to zero, and all the changes in length go back to zero. Like here, if you apply the load, it will change in length, but if you release the load, it will go back to its original length. So we call this perfectly elastic, very simple and clear. What about perfectly plastic? This is perfectly plastic. We can model it with the block on the rough surface. When we apply the load, you have to increase the load to such a degree that you overcome the friction on the surface, the frictional forces on the surface, and then it moves. Like here, if you apply this much stress, nothing happens. This much, nothing happens. But if you apply this much of stress, it suddenly starts to move, and you don't need to apply any other loads. Of course, this is an ideal model, but it's very good model. Surprisingly, it gives very good results. So this is rigid, perfectly plastic. Why we say rigid? Because here, whatever stress you apply, nothing happens. It's rigid. Until you reach this point, then plastic deformation occurs. In fact, you don't have any elastic deformation here, like here. It's not like that. It's like this. Okay? So this is a ideal model for plastic deformation, and surprisingly, it gives very good results in most of the metal forming problems which we have a lot of deformation. Right. Now we go to a more sophisticated models. In here, Also is rigid, it's rigid because it doesn't move as much as you apply the stress, but once the stress reaches a point, then it starts to move, but its movement is not straight. So it's not like the previous one, which was perfectly plastic. It's not perfectly plastic, it's linear work hardening, because as you apply the load, you get certain amount of displacement, strain. But if you want more strain, you have to increase the load. So this gradient tan minus h, or arctangent h, means h is the hardening, means that you have a work hardening model. Okay, we can model it like this. If you put a block on a rough surface and a string in here, so that when we apply the load, it doesn't move. This doesn't move because this prevents it from moving. So once you reach that, it means P reaches a certain value, it starts to move. While this moving, this also moves, but it has a stiffness H, like that. So you have this gradient here, okay? Because if you didn't have this, then it would be just a straight line like that. Another model which we use is elastic perfectly plastic. Now I should mention that for this model and the previous one in the previous slide, these are used for plastic deformation, like metal formings, bulk formings, like rolling, extrusion, forge, this kind of things. We use these models. But here we have another model which includes elastic. So this is an elastic, perfectly plastic. That's elastic, that's perfectly plastic. It means that when you increase the load, you get some elastic deformation until you reach a certain value, then you get plastic deformation without any hardening. So it's connected in series. That one is connected in parallel. Okay, this one is connected, these two are connected in parallel. This one, these two are connected in series. Therefore, when you start loading, this one moves like that. And when this one reaches a certain value, like that, it has moved already. It has elongated already that much. And then this one starts to move. And we don't have any more elastic deformation, because elastic deformation is up to here. Okay? This is for solving problems in which we have elastic deformation as well, like bending of plates. For instance, if you bend the plate, it changes, it assumes a curvature by plastic deformation, but after plastic deformation we have some spring back which is elastic. So we must have a model which includes some elastic behavior, otherwise we could not predict the spring back. Okay, we will come to solve such problems later on. Now this is more sophisticated. Here we have elastic deformation like before, but here we have plastic deformation, not perfectly plastic, but linear work hardening. Okay, so in another model we can have elastic and non-linear work hardening as well, but here I have tried to show you simple models. Okay, again here I have this block, this spring, and this spring. So block and spring are connected in a series, and with this spring in parallel. This means that when I move this P, of course this is E minus H, because E is that, H is that. When I move this spring moves. Okay, also this spring moves. So when I reach that point, P reaches that point, then plastic deformation starts. This is plastic deformation. Okay, these springs represent elastic deformation because when we unload, when we release the load, these springs go back to their original place. But once we move this block and release the load, then this block won't go back to its original place. So that's why it models the plastic behavior. Here again we are showing you a curve of variation of force or load against the change in length. In fact, this is the first data you get from a tensile test. Okay, because tensile test is what? We apply the load, which is F, and we measure the change in length, which is delta L. So if we note down those points and plot them here, we get a curve like that. This is for mildest thing. Now it says at point of maximum force on the diagram, because as you know we get a maximum point and then the necking starts and then it starts to drop, okay, for further plastic deformation. So this is maximum point, UTS, ultimate tensile strength. Of course here is the ultimate force. Now it says at maximum force, if you draw a line, it will draw a line tangent to P. That tangent will be parallel to delta L. Okay, will be parallel to delta L. Therefore, dF is equal to 0 at this point, which is point of maximum. Right? You know, when we want to get the maximum or minimum point for a function, we differentiate it and we put it equal to 0. That's what we have done here. That is the maximum point. Therefore, dF, the differential of f, is 0, because that's the function in terms of delta L. Right. But what is f? F is sigma A, stress times area. And if we differentiate this, because this dF, so here we have dF, d sigma A, sigma dA. Okay, that's what we have written here. And dF we said is equal to 0, so this is equal to 0. And what do we get from here? We get this relationship. D sigma to sigma is equal to minus dA over A. And of course we say that in plastic deformation the volume is constant. If the volume is constant, it means A times L is constant, because what we have done in tensile test, here we have assumed that we have a rod of length L and area, cross-sectional area A. Therefore V is equal to AL, that's the volume, and the volume is constant. Okay, if the volume is constant, then there is no change in volume. That means dV is 0. So what is dV? dV is dA times L, A times dL. Okay? And from here we get another relationship, dA over A equal to minus dL over L. And we had this relationship here and this relationship here, there. Therefore, from these two, we get d sigma over sigma minus dA over A, and minus dA over A is dL over L. Therefore, d sigma over sigma is dL over L. But dL over L, what is it? It's a strain. It's an increment of a strain. Okay? So, we get here like that. D sigma over sigma is d epsilon, or d sigma over d epsilon is equal to sigma. Right, what is this bar we have put here? This bar? This bar means, because when we have a tensile test, sigma bar is equal to sigma 1. But when we have other kind of loadings, in which we have sigma 1 plus sigma 2 plus sigma 3, still this behavior holds. In other words, this sigma bar is an effective stress. Okay, how do we get effective stress? We will see later on how we can calculate sigma bar in terms of components of sigma in x direction, y direction, z direction, or principal stresses. We will see how we get that. But this is the effective stress. It means that if a body is acted upon by different loads in different directions, we get different stresses. But we can average them out by writing out sigma bar. So this sigma bar is called effective or representative or average stress. Also, epsilon bar is the same thing. Therefore, this one is the same as this. This is for the tensile test. This is for any plastic deformation. Okay, sigma bar, the sigma bar, the epsilon bar. So what is it? This is the condition for instability, because instability starts at maximum point after this necking occurs. So that's the start of the instability. So if you have a function for sigma bar and in terms of epsilon bar, then you can find from that function where the instability occurs. Obviously, in tensile test, we can simply say that it's maximum point and we can find it. But in complicated cases, which is the most cases in the practice, in industry, you have tension or sigma applied at different directions. And therefore, you have to have a formula for finding this point in those loading conditions. And that's what we have in here. We'll come back to this later on. We can show that for a stress-strain curve, that is f over a, that's delta over l, or ln l over L0. And what we can see here is that this is a true stress-strain curve, and where is the instability? We don't know which point it is, but from this we can find out. If you make a tangent at this curve so that its intercept with the epsilon axis is such that from here to there is equal to unity, then this will be sigma, and the tangent, arc tangent, d sigma d epsilon is equal to sigma. Otherwise, in this triangle, tangent is equal to sigma over 1, which is sigma, and tangent of this is d sigma over d epsilon. So that is the condition from which we can find the point of instability. What could one get out of tensile test? So far you can see we can get a lot of things out of tensile test, haven't we? We have. And for engineering strain, now here we want to see engineering strain, because so far we considered the true stress strain. Now we want to see about the engineering strain. Now then, a strain d epsilon from 0 to e to epsilon, 0 to epsilon, d epsilon is equal to dl over l 0 to l, and we get obviously here ln l over l0, because the epsilon is dl over l, and changing length is L0 to L. So from L0 to L, and then ln L over L0. This is the natural strain or true strain. So this is the natural strain. Epsilon, that is equal to ln L over L0, because this is 0 to epsilon, and we get epsilon here. E, which is the engineering strain, is equal to L minus L0 over L0. And therefore we get L0 over L0 minus 1. Now we note that we have here L over L0. Therefore we can write L over L0 is equal to epsilon plus 1. E, sorry, that's E. That's the engineering strain. E plus 1. Then epsilon, which is this, ln L over L0, L over L0 is 1 plus E. Therefore, ln 1 plus E. And then d epsilon over dE is equal to 1 over 1 plus E. And because this is a transformation between natural strain and engineering strain. Now d sigma over dE is equal to d sigma over d epsilon times d epsilon over dE. Now we obtain d epsilon by dE here, and we had d sigma by d epsilon for the instability condition. It was sigma over 1. So sigma over 1 and 1 over 1 plus E times each other becomes sigma over 1 plus E, and we call that sigma 0. Therefore, because before d sigma by d epsilon was equal to sigma, so here d sigma by dE we call it sigma 0, because this is engineering and this is engineering. This was true, and this was true in strain, and this was true stress. So that is engineering stress, engineering strain. So we obtain this kind of relationships, and then we know that sigma is equal to F over A, and sigma 0 is F over A0, and volume constancy means that at every stage of the tensile test, the volume must remain constant. So at the beginning of the test, we have this volume, and at some point in the test, we have this volume, which are equal. Therefore, we can write A0 is equal to L over L0, and L over L0 is 1 plus E. Therefore, A times 1 plus E. And sigma 0 is F over A times 1 plus E, and sigma is 1 over sigma over 1 plus E, right? Because F divided by A is sigma. And clearly, for sigma against E, engineering strain, we get another curve like this, which is very similar to the previous curve, except that this axis is E. And here you can see that sigma 0 equal to d sigma over dE is equal to sigma, and then sigma 0 is sigma over 1 plus E. Otherwise, d sigma over dE is equal to sigma over 1 plus E. That is the instability condition. But here we haven't plotted sigma 0. We have plotted sigma against E. It doesn't matter, because we have a transformation of sigma 0 to sigma. So if d sigma over dE, which is for instability should be sigma 0, equals that, it means we have reached the instability. So if you put a tangent there, and the intercept here should be 1 plus E. Sigma divided by, here look, sigma divided by 1 plus E. Sigma divided by 1 plus E. That gives the instability point for this kind of, for engineering strain. The other one gave the instability point for true strain. Okay, so this is true stress, engineering strain. That previous one was true stress, true strain. Now then, here again we have this plotted sigma, epsilon, and S and E. S, of course, is sigma 0, and E is the engineering strain. This is engineering strain, this is engineering stress. This is true strain, this is true stress. Besides sigma, we have plotted d sigma over d epsilon as well. So you could see that this blue line is sigma, and this line is d sigma over d epsilon. But we have just proven that if sigma equals d sigma over d epsilon, that is the point of instability. So another way of obtaining the point of instability is to plot these two curves. The intersection of these two curves gives you the point of instability. It means that if you apply such a stress, you get such a strain, and that would be the point of instability, and after that necking occurs, so you mustn't go over there. Now, why is this point of instability so important? What does it mean, instability? You know, it's important because in plastic deformation we want to be in control of the plastic deformation. After the point of instability, everything is out of control. I mean, you have plastic deformation while the stress is decreasing, while the load is decreasing, in fact, and you cannot control it. So in metal forming problems, you get wrinkling, you get tearing, and these kind of things. So I will deal with this later. Now here again we have shown this in compression. Of course, I had shown this before. You know, tension goes like that, compression goes like that. Okay.